Hall thrusters are now the most widely flown propulsion system in space. Their ideal combination of electrical efficiency and specific impulse has made them widely used in satellite station keeping, interplanetary science missions, and will even power the Gateway space station set to orbit the moon. Hall thrusters utilize electric and magnetic fields to ionize and accelerate gases such as xenon to extremely high speeds. This means that Hall thrusters can achieve much higher fuel efficiency than traditional chemical rockets, which has proliferated their use. As Ben Jorns, expert and professor of electric propulsion, once put it, chemical systems are like the Hummers of space, whereas Hall thrusters are more like a Prius. While Hall thrusters are more efficient than chemical systems, they still have lost modes that sap performance. My research focuses on understanding these lost modes so that we can build better devices. Let's take a closer look at a Hall thruster to better understand what these loss processes are. The key components of the Hall thruster are the cathode, which sources electrons to the main discharge, and the anode, which is positively biased and sources neutral gas. Electrons are trapped in the radiomagnetic field on their path to the anode. These electrons vigorously ionize the neutral propellant, which is accelerated to high speeds by the applied electric field between the anode and cathode. The first loss mode is due to beam divergence. Ion velocities must be axial to contribute to useful thrust. We characterize the beam divergence with a divergence angle theta d. This quantity is measured by sweeping a Faraday probe azimuthally around the thruster to collect ion beam current. The ratio of the axial to radial current is then the divergence. The next loss mode arises from processes that sap energy from the electrons in the channel. Ideally, we'd like to couple all the power of the thruster directly into ions to produce thrust. However, Hall thrusters require high temperature electrons to efficiently ionize the propellant, which introduces loss modes. Electrons lose energy to the anode and channel walls, and from excitation and ionization collisions. We back out this loss mode by measuring the total ion current to the swept Faraday probe. By comparing this current to the total discharge current, which we call the beam efficiency, we can then estimate the electron loss current. The third loss mode is primarily driven by the voltage needed to extract electrons from the cathode to the main discharge. This voltage is unusable to accelerate ions and thus is a loss. We measure this loss mode with a retarding potential analyzer. This probe uses a series of grids to estimate the average acceleration voltage of the ions. The ratio of the acceleration voltage to the discharge voltage forms our estimate. The last loss mode results from incomplete ionization of the neutral gas. Neutrals must be ionized for the electric field to exert a force. As a result, slow-moving ionized gas reduces the fuel economy. We estimate the mass flow rate of ionized gas with the Faraday probe and an E-cross-B probe. The ion current is proportional to the ion mass flow rate, and the ratio of the ion mass flow rate to the total mass flow rate is the mass utilization efficiency. Understanding all these Hall thruster loss modes and how to measure them is a key step towards improving the overall device efficiency. At the University of Michigan's Plasma Dynamics and Electric Propulsion Laboratory, we employ these techniques during our experiments to better understand the underlying physics. Thanks for watching, and make sure to check out more videos on our channel.